In this video, we'll be talking about different theorems that are related to the tangents, to lines that are tangent to circles, and then the chords within a circle. So let's just review really fast what a tangent and a chord is. So a tangent is any line that touches a circle at exactly one place, and that point is called a point of tangency. And then a chord is just any segment that basically is inside of a circle. The endpoints are on the circle. And chords are kind of just, they can be any, there's not anything super special about them. They can be anywhere in the circle. So first let's talk about some chord theorems, then we'll get into tangents. So here's a theorem. If you have two chords that are passing through a circle, like I have chord AC and chord DB here, the measures of the angles that are formed by the two chords that intersect inside a circle are equal to the average of the measures of the intercepted arcs. Okay, so that is a lot of stuff. So let's break that down and see what it's talking about. So let's first look at just this picture and remember that angles 1 and angle 3, they're vertical angles, so they're congruent to each other. And angles 2 and 4 are also vertical angles, so they're congruent to each other. And we see that equality over here, showing that the measure of angle 1 and angle 3 are the same, as well as the measure of angle 2 and the measure of angle 4. So let's just look at angles 1 and angles 2. So what I need to look at is the intercepted arcs. So I have these nice, let me do them in a thicker red, these nice intercepted arcs AB and DC. And remember that we measure our arcs in degrees. So what this theorem says is that if you take the average of those two degrees, those two arc measures, and in order to find the average, you would add up their two measures and then divide by 2. That's going to be the same as the measure of angles 1 and angles 3. So angle 1 is the same as angle 3 is the same as the average of the arcs. Same thing with 2 and 4 and their arcs. So let's go ahead and maybe just do an example of using this. It's kind of a wordy theorem, but it works out to be pretty nice for us. So let's go ahead and look at example A. We are trying to figure out how many degrees is this angle inside of the circle X, this angle labeled X. So here we know two arcs. We know an intercepted arc AB and the intercepted arc DC. So what I'm going to do is I'm going to find the average of those. So I'm going to take 116, add it to 10, and then divide it by 2. So 116 plus 10 plus 110 is going to be 226 divided by 2, which is 113. So that means that 113 degrees is the average of those two arc lengths, or those two arcs. So that, based on our theorem, that means that both of these angles right here, angle X and the angle across from it, are 113 degrees. Okay, press pause and try the next one. Okay, so I have work shown right here that tells me that the angle is 60 degrees. But the angle that I found when I found 60 degrees is actually not the angle I'm looking for. That 60-degree angle is that angle that makes the arcs of 40 degrees and 80 degrees. So what I need to do is I need to look at, okay, if I know that those two angles are 60 degrees, is there a way I can figure out what X is? There is. Because we know that, I'm going to draw with a red line, this is a straight line right here. It means that 60 degrees plus whatever X is has to equal 180. Okay. So what I'm going to do is I am going to say, okay, if I take 180 degrees and subtract the 60 degrees that I already know, I'm left with 120 degrees. And that is my measure for angle X. Okay. So we've done a couple examples where we're using the arc measures to find the angle in the middle. And now let's work the other direction. Let's say we know the angles in the middle and we want to know the arcs on the outside. So in example C, I have a 50-degree angle right here in the inside of my circle, which means that this angle across from it is also 50 degrees. So we know that those two 50-degree angles are equal to each other. We also know that they're equal to the the average of these two arcs, so the average of 75 and x. So I'm going to set up an equation because I know 50 has to be equal to the average of 75 and x. So to find the average of 75 and x, I would add them together and then divide by 2. Then I just need to solve this equation. So what I would do is I would just think about getting rid of my denominator first. So if I have a 2 on the bottom of my fraction, I'm going to multiply both sides of my equation by 2. So that fraction just goes away. Then I have 2 times 50, which is 100, equals 75 plus x. I'll subtract 75 from both sides to get the x by itself, and x is equal to 25. So x is equal to 25 degrees. And again, that x value is an arc measure. So this x out here is 25 degrees. Okay, let's try it again over here. This is actually a very similar problem where we know that the angles inside right here are both 122 degrees. And we know that 122 is going to be equal to the average of my arc measures. So 114 plus x divided by 2. I'll multiply both sides by 2 with the purpose of getting rid of my fraction. That gets me 244 is equal to 114 plus x. Subtract 114 from both sides. Now we just have x is equal to 130 degrees. So then that arc length, or that arc measure, is 130 degrees. Okay. If you need more practice with this theorem, take a minute and practice it some more. We're going to move on and talk about something a little bit different called an inscribed polygon. So we've already talked about something that's inscribed. Last time we talked about inscribed angles, which deal with angles whose vertices lie on the circle. An inscribed polygon is just when you take a whole shape or a whole polygon and you put it inside a circle. Now the big rule is that all of the corners of your shape have to lie on the circumference of the exact same circle. So like here, this inscribed triangle, there's 3 points, there's 3 angles, and all 3 of those angles lie on the circle. We also have an inscribed quadrilateral. Remember that a quadrilateral just means it's a shape with 4 sides. This is kind of a random quadrilateral. There's also squares, rectangles, diamonds, kind of fancier ones. So let's go ahead and take a look at some theorems about inscribed polygons. So if you have a quadrilateral that's inscribed in a circle, then its opposite angles are supplementary. So let's remember what supplementary is. That means they add up to 180 degrees. So what we're saying is opposite angles add up to 180 degrees. So if I were to write that in symbols, I would say, okay, I'm going to take the measure of angle E, I'm going to add it to the measure of angle G, and I don't know what E and G are, but I do know that when I add them together, I'm going to get 180 degrees, because they're opposite angles. And I can do the same thing with the other pair of angles. The measure of angle D added with the measure of angle F is going to give me 180 degrees. Those 2 angles are supplementary. Go ahead and solve some problems like this. So if I'm looking at example A down here, I have an inscribed quadrilateral because all of the corners are laying, or all of the vertices are laying on the circumference of the circle, which means I know that the opposite angles are going to add up to 180. So 113 and y, those go together, and added together they give you 180 degrees. So let's just solve for y really fast. So those 113s are going to cancel each other out, and y is going to be equal to 180 minus 113, which is 67 degrees. Then to solve for x, I'm going to look at the other pair of opposite angles, the 70 and the x. So 70 plus x is going to be equal to 180. I'll subtract 70 from both sides. So x is equal to 110 degrees. So then these 2 degree measures would be my answers. So we're going to take a second, work on B and C. I'm going to let you guys do those ones on your own. I'll press pause, fill them in, and then just come back and check your answers. Okay, as you work through those, you should have gotten the answers that I have listed here for the x and y values of each. Let's talk about some different theorems. So we've talked about a theorem about inscribed quadrilaterals. Now let's talk about some theorems that have to do with inscribed triangles. So I have two here, and they're very similar. The first one says, if a triangle is inscribed in a circle, and one side of the triangle is a diameter, then it is a right triangle and the diameter is the hypotenuse. So if you look at that picture over here on the right, you'll see AB. That is your diameter. So what your theorem says is that if you've got some triangle that's inscribed in a circle and one side is the diameter, we know that that triangle is a right triangle. And we also know that the diameter is the hypotenuse. We can also kind of work the other direction. So say I have a right triangle inscribed in a circle. Say I already know it's a right triangle. Then I know that the hypotenuse is a diameter of the circle. Okay, so we can use this both ways. Either we can use it to identify that there is a right triangle, or we can use it to identify what the diameter is. So let's take a look at some examples of using these theorems. Let me zoom in on these two especially. So we're going to find the values of x and y in circle P. So first I want to look at some important parts of this triangle. First of all, it's inscribed, which is good. And I recognize this line right here as a diameter. So that automatically tells me that I've got a right triangle. So this x over here, that's going to be my 90-degree angle. The reason I know the x is the 90-degree angle is for two reasons. One, it looks like a right 90-degree angle, much more than the y angle does. And because I know that the diameter is the hypotenuse. So that means that the angle across from the diameter has to be the right angle, or 90 degrees. Now I've got to figure out what y is. So now I have to think back to what we know about triangles. There's always 180 degrees in every triangle, which means that if I were to add all these up, 52 plus 90 plus y, those should all equal 180 degrees. So I'm just going to go ahead and subtract 52 and 90 from 180. And let me grab my calculator so I can do that. 180 minus 52 minus 90, which leaves my y angle to be 38 degrees. Let's look at the next one. The next one looks really kind of smushed, but it's going to play out the same way of the one we just barely did. So first of all, let's identify the diameter that we have here. So we have a triangle, and then this blue line that I'm drawing, that's the diameter of the circle. So we know we have a right triangle. Okay. We also know that the angle that's across from that diameter is the right angle, which means that this angle up here that's across from the diameter, that's the right angle. So x is equal to 90 degrees. Then to figure out what y is, we can use the same thinking that we used in the previous question to think about how we know that all the angles in the triangle are going to add up to 180. So if I have a 90-degree angle and an 80-degree angle, I'm just missing 10 degrees to get to my 180. Okay. Let's go ahead and take a look at this one. This one's a little tricky. So let's start by identifying that we have a diameter, which means we have a right triangle, and y is my right angle. So y is 90 degrees. That's the easy one. Now this next part's kind of tricky because our other two angles, we don't actually know either of them. One is x and one is 2x. So what we're going to do is we're just going to set up an equation that says if I were to add up all the sides of my triangle, all the angles of my triangle, I better get 180 degrees. So x plus the 2x plus the y, which I know is 90, is going to be 180 degrees. Then I'm just going to start solving this equation. So I'm going to subtract 90 from both sides. So I have x plus 2x is equal to 90 now. If I take x and 2x and add them together, that's 3x. So 3x is equal to 90. Divide both sides by 3, and I get x equals 30. So in this case, our x is equal to 30, which means that this bottom right angle in my triangle is 30 degrees, and the top right, or sorry, bottom left is 30, top right is a 60-degree angle. Okay, so with each of these problems that we just barely did, we were using just one of the theorems from above. We're using the fact that if we know that we have a triangle that's inscribed and one of the sides is the diameter, then we have a right triangle. So let's work the other direction. Okay, well we can look at each of these the other direction as well, and we can think, okay, if we have a right angle, like say I knew that this angle over here, x, was a right angle, then I could claim that that hypotenuse was a diameter. Okay, all right. So this next section is just kind of mixing a bunch of problems together. So we're going to use as much as everything that we know about angles and arcs and inscribed polygons to fill in the missing arc length or arc measure. So the first one's going to look really similar to what we just barely did. I have a diameter, right? So I have a right angle. And I'm just going to go ahead and outline in red the piece that we're trying to figure out. I'm trying to figure out what this angle x is. Now I know something about that arc length x. Is that arc, because that arc is called an intercepted arc, and it is related to the angle JGH. So if I could figure out what this angle is up here, it would really help me to figure out what the arc length is. So let's start by just figuring out what that angle is at the top left corner of my inscribed triangle. So I'm going to say I have 180 degrees. I'm going to subtract the 90-degree angle and the 53-degree angle, and I get 37 degrees. So this angle up here is 37 degrees. Now what I have to remember is that whenever I have an inscribed angle like that, the intercepted arc is twice that measure. So that means that if I take 37, multiply it by 2 to get 74, that's going to be my x value. Okay, let's go ahead and move on to the next one. I'm again going to highlight in red the piece that I'm looking for. So I'm trying to find the measure of that arc, the arc DC. Now there's a couple different ways that I might be able to think about this, about finding this, but here's one way. If I could figure out what the measure of angle DAB was, that would tell me what the measure of the entire arc DCB is. And I already know that one chunk of my arc is 58 degrees. And I could use that to figure out what my other chunk of my arc is. So let's just work back through that step by step. So let's say I want to start by figuring out what is angle DAB. Well, I know that in inscribed quadrilaterals like this, opposite angles are supplementary. So that means that 97 plus that angle, maybe we'll just call it A for angle, that has to be equal to 180 degrees. So I'm going to subtract 97 from both sides here, which tells me that my A is equal to 83 degrees. So I'm going to come back up to my circle. I'm going to put that information in. I know that A is 83 degrees. So let me actually write that out in symbols. Angle DAB, the measure of it, is equal to 83 degrees. So that means that the measure of my arc DCB is twice that amount. So 83 times 2, it's going to give me 166. That's the measure of that arc length. Now, I don't care about the measure of angle DCB, but I do care about the measure of just the arc DC. So in order to figure out what that is, I'm just going to take the 166 degrees, subtract the 58 degrees that is already there, and I will get 108 degrees. And that is going to be the value of x. So it basically means that if this red arc is 108 degrees, and then this black arc right here is 58 degrees, together they create that 166 degree arc that I need. Okay, let's take a look at another example down here. So we are trying to figure out what this arc measure is over here on the right. And we're going to look for it in degrees. And we've got some information about an inscribed triangle. So let's first see what we can figure out about this triangle. So I'm going to take this 75 degrees, which represents this arc right here. And I'm going to use that to give me what this angle is at the top, angle Z. Remember that your intercepted arcs are always twice the inscribed angle, which means that this inscribed angle is 37.5. I'm going to use all of that to figure out what the third angle of my triangle is. Because I know the angles of my triangle have to add up to 180. So I'm going to take 180, subtract 49, subtract the 37.5. Oops. And this angle right here on the bottom left is a 93.5 degree angle. Now here's what's nice about that. That 93.5 degree angle, that is the inscribed angle that creates the intercepted arc that I'm looking for. Which means that my intercepted arc is going to be 2 times that nice angle I found, which is equal to 187. So my intercepted arc is 187 degrees. So again, with these problems, there's not really like a, let me tell you, a formula and like a number of steps to follow to find these measures. You just need to look at what you have and what you can figure out, right? Use your theorems, use what you know about inscribed angles, inscribed polygons, everything like that, so that you can find out as much information as you can. Okay, let's jump and talk about tangents. So remember, a tangent is a line that touches a circle at only one point. So here are 2 theorems about tangents that we are going to use. The first says that if a line is tangent to a circle, then it's perpendicular to the radius drawn at the point of tangency. You can see that in this picture over here. We have this line L that's tangent to the circle, and that line is making a 90 degree angle with this radius BC. Okay. We also have another theorem that's really similar. Okay, it says in a plane, if a line is perpendicular to the radius of the circle at its endpoint, then the line is tangent. So it's basically working the other direction. So in the first theorem, it's saying if you've got a line and it's tangent to the circle, then you know there's some perpendicularity there. In the second theorem, it's saying, hey, if you can prove that those 2 lines are perpendicular, then you know that that line is tangent to the circle. So let's go ahead and use these theorems to answer some questions. In these examples, we are finding the length of the missing segment. And here's an important key here. We are assuming the segments that appear to be tangent on the circle are actually tangent. So like if you look at example A, this piece, well, let me do it in red so you can see it a little bit better. This piece right here, this piece of the triangle, that looks like it's tangent to the circle. So we're going to assume that it is. So how are we going to solve for this missing side length? It's actually not too hard. What we're going to do is, since we know it's tangent, we know that it creates a right angle right here. So now I have a right triangle, and I know 2 of the side lengths, and I'm looking for the third. So I can just set up the Pythagorean theorem here. A squared plus b squared is equal to c squared. Remember that the a and the b are always the 2 legs, or the shorter sides of my triangle. And then the c is always the hypotenuse. So let you go ahead and work that one out on your own. So hit pause if you need a minute to work that one out. But you should get 19.4 is equal to, oh, that's a super messy 4. 19.4 is equal to c. Or is equal to question mark in this case. And that's your missing length there. All right, let's go ahead and take a look at another one. So we are going to assume that this line that looks to be tangent is actually tangent. So it forms a right angle here. One thing I want to point out to you here, this looks maybe a little bit weird, right? The way these are labeled, this 2 is labeled just for the bottom half of this circle. What that 2 is telling us is that 2 is just the distance from here to here, so it's just the radius. Which means that this other side is also going to be 2, which makes this whole side of the triangle 4. So I just started thinking about trying to find that missing side of our right triangle. One of our side lengths is 4 squared. Well, one of our side lengths is 4. The missing side length is a leg, so I'll just call it B for now. And then we know the hypotenuse is 5 squared. As you work through this, you're going to get that B is equal to 3. So that is the missing side of that triangle. Okay. I'll let you guys take a minute and work through the other two on this page if you want. I'll hit pause, fill them in, and then come back and check your answers. Okay, maybe you got stuck on C, so I'm here to kind of help you finish that one off. You probably started this way. You found your right triangle, you set up the Pythagorean Theorem, and then you found that your missing side length for your triangle is C. So this whole blue side that I'm highlighting right now is 20. Now, unfortunately, that's not actually what this question wants. This question wants to know how long is just this piece. So what we're going to do is we're going to use the fact that all of the radii of a circle are the same. So if this radius right here, that's part of our triangle, is 12, then this radius right here is also 12. And if the entire length of my triangle is 20, it means that my question mark right here is just 8, because 8 plus 12 will give you 20. Okay, we're going to have to use a similar kind of idea with our next problem. So here we have a right triangle because we have a segment that's tangent. And so we want to use the Pythagorean Theorem to find that missing side length. But unfortunately, I only know one side of my triangle. I know that that side of the triangle is kind of broken into two pieces, 8.4 and 5.6, which means that the total length of this side of the triangle is 14. So that's nice, but I still need one more side length. And in fact, I actually know this side length right here, because this side length is a radius of the circle, just like this 8.4 is a radius, which means that this other side of my triangle is 8.4. So now I have enough information that I can set up an equation. 8.4 squared plus b squared is equal to 14 squared. So as you're working through these, you really want to make sure that you are looking at the right pieces of the triangle. When you solve that, you're going to get b equals 11.2. All right, now let's look at these last two examples. These ones are some really interesting ones. I really like these ones. What we're trying to do is we're trying to determine if AB is tangent to the circle, and we have to explain our reasoning. And our explanations are going to look like a bunch of math equations, okay? So what we're trying to do is decide, is this AB tangent to the circle? Now here's what we know. If it is tangent to the circle, then we have a right triangle. If it's not tangent to the circle, then it is not going to be a right triangle. So what we're going to do is we're going to check to see if the triangle we have is a right triangle. And one way we can do that is we can use the Pythagorean Theorem again. Remember that the Pythagorean Theorem only works on right triangles. So here, in example A, we have all the sides of our triangle, A, B, and C. So what I know is if I plug in all those numbers where they belong, so 12.6 squared plus 9.9 squared is equal to 16.5 squared. If this equation is true, then it's going to be a right triangle. If it's not true, then it's not going to be a right triangle. So let me work through this a little bit slower for us. First, what we're going to want to do is we're going to want to square all of our numbers. So we'll have 158.76 plus 98.01 is equal to 272.25. Now I'm going to add those two numbers that we see on the left side of the equation. When I add these two numbers together, I get 256.77. Now, what I have written down here says 256.77 is equal to 272.25. Now, is that equation true? No, that is a lie. Those two equations are not equal to each other. So we'll often use this not equal to sign. It's an equal to sign with a slash through it, to say that those are not equal to each other. So what happens is we just broke the Pythagorean theorem. Okay? Well, we didn't break it, the triangle broke it. So that means that this triangle is not a right triangle. And since it's not a right triangle, we know that AB can't be tangent to the circle. Because if it was tangent, it'd be a right triangle. So that's how we can prove if that segment is tangent to the circle. Okay, let's look at this other example. I'd invite you to hit pause and try this one on your own first, if you feel ready for it. What we need to do first is fill in all the sides of our triangle. So I'm going to go ahead and fill in this side right here as 3.2 because it's a radius of my triangle. And then I'm also going to figure out how long is that hypotenuse of my triangle. This side of my triangle, when I add those two numbers up, is going to be 6.8. So now I need to see if this triangle passes the Pythagorean theorem test. So is 6 squared plus 3.2 squared, is that equal to, I want to put a little question mark over that, is that equal to 6.8 squared? So I'm just going to use my calculator to make this a little faster. I'm just typing in that whole left side of the equation. 6 squared plus 3.2 squared. That's 46.24. And then I'm going to figure out what 6.8 squared is. Oh, would you look at that? 6.8 squared is 46.24. So what happened is that the Pythagorean theorem worked, which means we have a right triangle. And if we have a right triangle, that means that yes, the segment AB is tangent to the circle. Okay. So hopefully this has helped you guys to get an idea of how we can use some of these really important theorems about chords and tangents to answer some good questions about circles.